Hello and welcome back. Well, in today's class, we'll be starting with a new chapter that is chemical thermodynamics. What is thermodynamics? Actually, thermo means heat, dynamic means motion. So, this is the branch of chemistry that basically deals with the movement of heat from one part of the system to another part, or from system to surrounding and surrounding to system. So, suppose I've got a test tube, and in that test tube, I'm carrying out a chemical reaction. And suppose the reaction is exothermic, so test tube will become hotter. That means the hotness of the test tube is showing me that the reaction occurring in the test tube is an exothermic reaction. If it becomes cool, that means the reaction occurring is an endothermic reaction. So the movement of heat is basically giving me an idea about the reaction. So chemical thermodynamics is the branch of chemistry that basically deals with the movement of heat during a chemical reaction from system to surrounding and vice versa. So first thing we'll see here is system. So first point is system. We'll see what does a system means. Well, a system is a part of universe under thermodynamic consideration. Any part of universe under thermodynamic consideration is known as system. For example, I gave you an example of a test tube. In that case, test tube is my system. So any part of universe under thermodynamic consideration is a system. It can be a test tube, it can be a room. In summer, we try to cool a room in which we are sitting by putting air conditions or something like that. In that case, system becomes that room, rest whole universe is surrounding. When we talk about global warming, planet Earth becomes our system. When we say that ultraviolet radiation from sun come to Earth and the greenhouse gases does not allow infrared radiation to move out. As a result of that, the temperature of the Earth is continuously increasing. Then in that case, planet Earth becomes system, rest whole universe becomes surrounding. So what is system? Any part of universe under thermodynamic consideration is known as system. We have three different type of systems. We can have open system, a closed system, and an isolated system. So open system, closed and isolated. Well, open system is what? It is just like a glass of hot water which can exchange energy as well as matter with the surrounding. You can see that in case you got a glass of hot water, you'll see that the vapors they are moving out as well as the heat is also moving out from system to surrounding. Such a system is an open system. So open system can exchange both energy and matter with surroundings. Same one glass of hot water, if you cover it with a lid, it can exchange heat but cannot exchange vapors with the surrounding. So a closed system can exchange energy but no matter with surroundings. Likewise, if we talk about an isolated system, if you put that one glass of hot water in a thermos or thermoflask, it can neither exchange energy nor matter with surroundings. So again, the part of universe under thermodynamic consideration is known as system. Rest whole universe is surrounding. We have three different type of system, that is open, closed and isolated. Open can exchange both energy as well as matter with the surrounding. Closed can exchange energy but no matter with the surrounding, and isolated can neither exchange energy nor matter with the surrounding. Now the question comes to our mind when we talk about all these things. What are the other thermodynamic properties? So before starting with the thermodynamics proper chapter, we'll see these thermodynamic properties. These properties can broadly be divided into state function, state functions, and path functions. So we have state functions and path functions. What does that mean? Well, there are thermodynamic properties which just depend on the initial and the final state of a system and does not depend on the path followed. Such thermodynamic properties are known as state functions. I give you one example. Say I burn carbon and it gets converted to CO2 and it gives out X kilojoule per mole of energy. Now I follow another path where I am burning carbon and I am forming carbon monoxide. The energy given out is say Y kilojoule per mole. Then I am burning that carbon monoxide again and it is getting converted to carbon dioxide. The energy given out is Z kilojoule per mole. You will notice that X is equal to Y plus Z. That means the amount of heat energy which is given out basically depends on the initial state and the final state. So it is basically depending that you are converting carbon to carbon dioxide, no matter whether you are converting in one step or you are following more than one step. Such a thermodynamic property is a state function. So a state function is something which depends on the initial and the final state of a system and does not depend on the path followed. I give you another example. Suppose here is state 1 of the system and here is state 2 of the system. My system is moving from state 1 to state 2 and it is following this path. This is path A. It can also follow this path. This is path B. It can also follow this path. This is path C. The change in state function is same because it depends on the initial and the final state of a system. I give you one raw type of an example. Suppose you are climbing the 4th floor of a building from the ground floor. No matter whether you are going through an escalator or stairs or by a lift, the height which you are traveling in all the cases is same because the height which you are traveling depends on the initial state from where you have started and the final state where you have reached. So that is a state function. It does not depend on how you have come to that particular floor. So likewise in thermodynamics also we have state functions. That means the change in the state function is same when you are moving from state 1 to state 2. That's why it can be differentiated. It can be divided into smaller part. Hence, a state function you will always see can be in a differentiated form like delta G, delta H, delta S, delta U. They all are state functions because they can be differentiated dG, dH, ds, du. They can be written in their differentiated form. However, there are thermodynamic properties which does not depend on the initial and the final state of a system but depends on the path followed. So here I'll show you that I'm drawing a graph between pressure and volume, and suppose this is state 1 and here I have state 2. Well, the thermodynamic work done, del W is always PdV, pressure into change in volume. Now in this case, when I'm moving from state 1 to state 2, suppose I am following this path. I'm moving like this. Then the work done is the area below this. So in path A, work done is this area. If I follow path B, the work done is this area. So it is changing with path. That means work done is a path function. It's not a state function. Since the change in work done is not constant when you are moving from state 1 to state 2, you cannot differentiate it. That's why small amount of work done is always represented by del. Since we cannot differentiate it, del will represent small amount of work done. Likewise, small amount of heat given out by the system is also represented by del Q. So heat is also a state function and it is also heat is also a path function and it cannot be differentiated. So it is also expressed in terms of del. So del basically represents that the given thermodynamic property is a path function. So this is what state and path function. Now the question comes to our mind from here is state of a system. What is a state of a system? State of a system. Well, many a time students, they give me answer that state of a system is solid, liquid or gas state. Well, solid, liquid and gas are not state, they are the phase. When we talk about state of a system, we'll see what does that means. We have an ideal apparatus, that is a gas cylinder. Suppose here I have a gas cylinder. This gas cylinder is fitted by a piston, airtight piston. And inside this gas cylinder, I have got a gas. The volume of the gas is say V1, its temperature is T1 and its pressure is P1, so its state is 1. If any of these value changes, the rest of the two value will also change. Suppose the volume is changing to V2, the temperature will become T2, the pressure will become P2, then the state is 2. Because you know very well P1 V1 by T1 is equal to P2 V2 by T2. So whenever a system, this is the definition of state of a system. Whenever a system has a particular temperature, pressure or volume, it is said to be in a particular state. If any of these values changes, the state of a system is also said to be changed. So this is state of a system. That means state of a system is depending on pressure, volume and temperature. That's why pressure, volume and temperature, they are known as state variables. So state variables are those on which the state of a system depends. That is temperature, pressure and volume. These are the factors on which state of a system depends. So they are state variables. Now we'll see fourth point, a thermodynamic process. Well, first we'll see what does a process means. Whenever a system changes its state, it is changing its state. It is coming from state 1 to state 2. Whenever a system changes its state, a thermodynamic process is said to take place. So whenever a system is in its initial state, then it is moving to the final state, it is changing from state 1 to state 2. That means a thermodynamic process is taking place. So whenever a system changes its state, a thermodynamic process is said to take place. Depending on that, we have different type of thermodynamic processes like isothermal process. An isothermal process is one in which the temperature of the system remains same. That means delta T is equal to 0. Change in temperature is 0. So in isothermal processes, you will have no change in temperature. The temperature will remain constant. Next we have isobaric. Isobaric. As the name suggests, isobaric means in which the pressure is constant. So these are the processes in which the pressure remains same. That means the formula over here will be V1 by T1 is equal to V2 by T2 since delta P is equal to 0. Next we have isochoric. Isochoric. These are the systems in which delta V is 0. That means there is no change in the volume. So your formula will be P1 by T1 is equal to P2 by T2. And the last one is adiabatic. Adiabatic process. In this, heat change is 0. So an adiabatic process is one in which heat can neither enter nor leave a system. That means an adiabatic process occurs in isolated system. So these are the four different type of systems. We got isothermal, isobaric, isochoric and adiabatic. Next, these thermodynamic processes can also be divided into two parts. In thermodynamics, that classification basically works. That is reversible and irreversible. Reversible and irreversible thermodynamic process. Well, a thermodynamic, whenever a process occurs, whenever a process is occurring, say learning is also a process in which when the students, they join you, that is the initial mental state of them. And when you teach them something, their knowledge get enriched. That becomes the final state of that particular day or that after that particular lecture. So there is a change in the mental state. So learning is also a process. When we talk about any process, no matter whether it's thermodynamic process or some other process, there are always two factors or two forces which are operating over there. One is the deriving force that derives that process, that try to do that process, and the another one is the opposing force. So there is a force that is trying to do that thermodynamic process, whereas there is a force that is trying to stop that process. So we have two different forces, deriving force and opposing force. So whenever the opposing force is nearly equal to that of deriving force, or we can say the deriving force is only slightly greater than the opposing force, that is a reversible thermodynamic process. In that, suppose both the forces they are nearly equal, in that case the thermodynamic process will occur in both the directions. So likewise, here in this case, suppose I have got a gas in a cylinder, the external pressure, the atmospheric pressure is nearly equal to the internal pressure. Or I can say the internal pressure is nearly equal to that of external pressure. It is only slightly greater than the external pressure. If it is slightly greater than the external pressure, the gas will slowly expand. The process will occur extremely slowly. Slowly it will expand because the external pressure is preventing it from expansion. And it may happen that it is expanding, then again it will contract. That will be in equilibrium. The piston will be in equilibrium. Like it happens in balance when both the pans they have same weight, they are in equilibrium. So here also the external and the internal pressure they are nearly equal. That's why the piston is in equilibrium. It keeps on moving up and down. That means a reversible process. Even if the gas is expanding, the rate of expansion is very slow. So if we talk about a reversible process occurs, it occurs extremely slowly. It occurs quickly. It occurs in both directions. It occurs only in one direction. I give example of irreversible process. Suppose the pressure inside the cylinder is very high as compared to the external pressure. The gas will simply expand. No compression, no reversibility. It will simply expand and it will expand quickly. So such a process occurs quickly, occurs only in one direction. Third, in reversible process, work done is maximum. Work done is maximum. There is no such relation. No such relation. Well, if the external pressure is nearly equal to that of internal, and if the gas is expanding, that means the gas which is doing the work is nearly, it is trying its level best to expand against a force which is nearly equal to it. That means the work done is maximum. Whereas in irreversible process, the internal force is very large as compared to the external force. So it is not doing its maximum work. I'll give you one example. Suppose we are playing a game of tug of war. In tug of war, the opposing side is say nearly equal to that of one side. I've got a team and I've got an opposing team. My team is only slightly stronger than the opposing team. Then we have to use our maximum power in order to pull them. That process will occur extremely slowly because the opponent they are equally stronger. So that will occur extremely slowly. It will occur in both the directions. And in that case, we have to do our maximum work. And suppose the other team is very weak. In that case, we are not supposed to do our maximum work. We'll just pull them and they'll come. The pointer will move towards our side. So that will be one-sided only. That will occur quickly. We are not doing our maximum work. But that doesn't mean that we are doing the minimum work also. So there's no such relation. So this is a basic difference between reversible and irreversible processes. Now we'll see thermodynamic work done. Next point, that is the fifth point, is a thermodynamic work. Thermodynamic work, as I have already told you, is represented by P delta V. We'll see how that comes. Again, the same apparatus. This is a cylinder. and the cylinder is fitted with an airtight piston. Here I've got an airtight piston, and in this cylinder I've got a gas. This gas has got some pressure. The external pressure of atmosphere on this is say external pressure, which is pushing this piston downward. Now when I'll heat it, I'll provide it some heat, that is del Q amount of heat. The gas inside the cylinder will expand. When it will expand, it will push the piston upward. So piston is moving upward. Say piston has traveled this distance. So dl is the small distance traveled by the piston. If area of cross section of the piston is A, then small amount of area of cross section of the piston is dA. Now you know very well that work is always force into displacement. It is always force into displacement. And you also know that pressure is force per unit area. So I can say force is equal to pressure into area. Now I'll put the value of this force here. The equation I will get is work is equal to pressure into area into displacement. We'll move on to the system now. So small amount of work done is always P for P external, because external pressure, that is constant, into area in this case is dA, into displacement is dl. We know very well that area into height is always volume. So del W is equal to external pressure into dV. So we can say the work done is P delta V, that is pressure into change in volume. This is work done. You have to remember the sign conventions also, because the sign conventions are of prime importance in thermodynamics. If del W is negative, this is expansion. Expansion means work is done by the system. If del W is positive, that means compression, that is work done on the system. Compression. Now we'll see work done in an isothermal and reversible process. That is extension of this. That is work done in an isothermal and reversible process. Isothermal and reversible process. Well, when I am saying isothermal process, that means maximum work done. As I have already told you, the work done in a reversible process is maximum. So we'll be talking about W max, that is maximum work done by the system. We'll derive equation from here. Del W, this is the work done by the system, is minus PdV. I am putting negative sign because work is done by the system. You know very well that PV is equal to nRT. So P is equal to nRT by V. I am replacing P by this. So del W is equal to minus nRT by V into dV. So del W is equal to minus nRT dV by V. It is in differentiated form, so we'll integrate it. That is W is equal to minus nRT integration of volume change from V1 to V2 dV by V. According to law of integration, work done is then nRT ln V2 by V1. I can convert this natural log to the log to the base 10. In that case, work done will become minus 2.303 nRT log V2 by V1. So this is the volume change from V2 to V1. We can call it maximum work done. So whenever you are asked to calculate the maximum work done, that automatically means the conditions are reversible and you will calculate the work done in reversible conditions. So work done in reversible conditions is minus 2.303 nRT log V2 by V1. You know very well that volume is inversely proportional to pressure. So in this case, we can also write work done maximum is also equal to minus 2.303 nRT log P1 by P2. So this is how you can calculate the reversible work. So we have done some of the thermodynamic properties here. That all we were scheduled for today's class. In the next class, I'll be talking about some thermodynamic properties like internal energy, enthalpy, first law of thermodynamics. This is what we'll be doing in the next lecture. If you have not subscribed my channel, please do subscribe so as to get all notifications on time. Thanks for watching. Thank you very much.